Kia ora tātou, welcome to this video where we'll introduce Punnett Squares. So in the last video we were looking at inheritance, and we saw that if we had a male and a female parent, a male and a female parent, depending on what alleles they have to begin with, the male would contribute one of those alleles to their offspring, and the female would contribute one of their alleles to the offspring. So we looked at the example that the male had the alleles of brown eyes and blue eyes, and the female had the allele of blue eyes and blue eyes. And so there were two different possibilities for what the new offspring would be able to inherit. So Punnett squares are a way of easily showing all of the different possibilities that offspring could have according to the genotype of their parents. So let's look at some examples. So if we say that we've got a parent who has the genotype of, and we'll still use BB, so their genotype is BB, and we'll say we've got a male who has a genotype of BB as well, capital B, capital B. Then what we do with the this Punnett square is that in each of these boxes here, we put one of the alleles that each parent could contribute. So I'm going to put the big B into that box and this B into that box, and then these ones there like that. So we just draw it out, B, B, and then B, B. And so these boxes here are reserved for the possibilities of the different offspring that these parents could produce. So the way we do it is we put this B here will go into this box and this box. So we put it B like that and B like that. This B here will go into that box and that box. So can you see it's just all in the same line? And then you can probably guess that this B is going to go across into that box and across into that box. So we've got B, B, and then this B is going to go in there, and this B will go into there. And so this has all got a bit messy now, so we'll just tidy it up. So we've got B, B, B. Excuse me, just taking a second. But you can see it doesn't take very long once you've got used to it. And so each of these boxes in the middle represents a potential fertilization event. So if there's four possibilities, so we could have this one, this one, this one, and this one as all individual fertilization events. And so each box represents a 25% chance that each of these things could happen. So there's a 25% chance that we could have BB, capital BB, capital BB, capital BB. And so we add them all together, and we can easily see that in this situation, the possibility of us getting an offspring that has capital B, so blue eyes, is actually 100%. There's no other possibilities. So the genotype ratio is, in this case, we're going to say 100% BB. And we can also, information we can get from this is the phenotype ratio. And in this case it is, because each of these offspring have got that same genotype, they're each going to have the phenotype of brown eyes. So we're also going to have 100% brown eyes. Nice and easy. So we can change the genotypes of the parents and work out what all of the different possibilities are that an individual offspring could have. So let's do a couple of examples. So instead of, let's get rid of all of this, instead of the male parent having capital B, let's make it so that they've got capital B, lowercase b. So in this case, we're going to put the capital B there, lowercase b there. So we'll go big B goes on that side, little b, and then we've got the big B there, big B there, big B there. big V there. So let's look at the ratios that these parents could potentially have for their offspring. So each box represents 25%. So we've got 2 times capital B's. So we're going to have 50% of capital B, and 50% for capital B, lowercase b. Half and half, and that's quite easy to see. And then the phenotype ratio, because each of these individuals have got a capital B with them, they all contain a dominant brown eyes allele, they're all going to have brown eyes. Even though they're going to have different genotypes, they will all have brown eyes. So the phenotype ratio is going to be 100% brown eyes. Okay, so let's do one more just to drive this home. There's only about 6 different possibilities that you can put together, so you can see if you can work those out. So let's put a B together. So we've got 2 heterozygous individuals. And what will that look like? Often, so I've been drawing it. Often you'll draw the capital letter first if there is one. So that's why I've changed the brown eyes B to the left hand side, because I know that there's going to be a lowercase b going after it. So we'll have B, and then... Okay, so this time we've got slightly different ratios. Here we have got 1 capital B, so the ratio would be 25% capital B. Or we could do this, we could show this as a ratio properly of going 1 capital B, to we have 2 of these capital B lowercase b's, so we've got 50%, because 25 plus 25, 50% capital B lowercase b, and equally we could do this as 2B, and then we've got 1 lowercase b, 25% lowercase b, so 1B, B. So that is our genotype ratio. You can draw it, you can show it like this, or you can show it with percentages like that. The phenotype ratio in this case is that all 3 of these, 1, 2, 3, they all contain a dominant brown eyes allele. So they are all going to have brown eyes. And this one here does not contain a dominant brown eyes allele, so that is going to contain, so that's just going to have blue eyes. So if each of these boxes represents 25%, then we can say 25, 25, 25. The phenotype ratio is going to be 75%. So if these 2 parents had offsprings, there would be a 75% chance for each offspring that the offspring would have brown eyes. But even though both of these parents would have brown eyes themselves, there is a chance, a 25% chance, that they could have an offspring with blue eyes. So we can equally show this as 3 brown eyes to make some space. Sorry, I've got to get rid of this. 3 brown eyes offspring to 1 blue eyes. So we can show our ratios with either percentages or the actual ratio symbols. So I hope this explains Punnett squares for you. Keep watching and we'll be working through genetic variation. Thanks very much.